Now that everyone's had a chance to settle down again, we're going to get started with this. So you can see the program here. First, I'd like to thank all of our sponsors, Arvin Cunningham from Idaho National Lab, Jesse Armagost from NextEdge, and Dan Markowitz from Micron, and Amy Mall from our own program here. Amy is down in Puerto Rico where? Costa Rica, at a conference. I was going to show the video of a big Mamba dance going on that she sent me, but I didn't. So, so she's having an alleged academic experience in Costa Rica. So, all right. So we got 4 talks here. They're all pretty different in terms of what they discuss. Everything from, deposition of ceramic coatings to go inside a semiconductor processing tool, how to work on equipment to improve atomic layer deposition, recycling plastic, as well as studying nuclear graphite. So a wide range of subjects. I think we're about ready to get going. So, is our first team ready? Sponsored by NextEdge.
All right. Hello, everybody. Thank you for coming. We are Team NextCap. I'm Sam. These are my teammates, Connor and Alex, up here with me. And our project was on the development and characterization of YOF coatings. Oh, sorry, we weren't ready. So a little bit about our sponsor. Our sponsor company was NextEdge, and they specialize in precision machining, surface modifications, and advanced engineering coatings for the semiconductor industry. Our professional liaison with NextEdge was Jesse Armagost. He's an ME alum from BSU. He's been an engineer at NextEdge since 2008, and he also sponsored a senior project last year. So a little bit of context, we're investigating coatings for the interior of dry etch chambers, and dry etching is a common process in semiconductor manufacturing that involves the removal of material by bombarding it with ions from plasma. These etch chambers are often ceramic coated to minimize erosion and the production of contaminant particles that can damage the wafers inside.
So a common material being used today in these dry etch chambers is yttria. And when yttria reacts with a fluorine-based plasma in these dry etch chambers, it creates a thin YOF layer, or yttrium oxyfluoride. And as this with this interaction, YOF particles will fall off the coating and actually contaminate, or can contaminate, the wafer inside, which is not desirable when you have these multi-billion industries that rely on these wafers to be pumped out. And so looking at, well, a different perspective is looking at YOF as the coating itself. Since it already has fluorine in the system, it's more resistant to the fluorine plasma, and as a result produces fewer contaminants onto the wafers. And so how the process works is, let me use the pointer here so people on Zoom can see. So I think that works. Yeah. So how this process works is that the current process today that's being used is plasma spray deposition. And as yttrium particles are accelerated or injected into this plasma arc, it is then molten and hit onto the substrate, and then this solidifies and densifies onto the substrate. And the issue with YOF is that this process is about 14,000 Kelvin, which is above the temperature for YOF. So as a result, it induces phase changes, and these phase changes are less desirable than just using yttria. So to actually use YOF, we have to look at a different process entirely. And this process that we use is called aerosol deposition. And this process takes place at room temperature, so there should be no phase changes present. And how it works is that in the carrier gas, and for us, we use nitrogen, it goes into where our powder is and aerosolizes our powder. And that aerosolized powder is then accelerated, focused at the nozzle, and accelerated towards the substrate as the substrate moves on the XY axis and is programmable. So with that, how the process actually works as the particle is accelerated at the substrate, as it hits the substrate, it will then hit and make this anchor layer by fracturing the moment it hits the substrate. And through this, it creates this anchor layer that's very dense and cohesive. And then as continual deposition occurs, it slowly creates a less dense layer, but it is still very cohesive. And so we want to see is right here, this green, where we have a medium velocity or medium particles. And as the particles are accelerated towards the substrate, they hit, fracture, and densify on top of itself. Well, if we have two high velocity or agglomerates, as they hit, it'll then spread out more so and create a more porous structure, which is not desirable for a protective coating, as well as two high velocity or large particles will just start to sandblast or abrade, or in a sense, sandblast the surface, and no film will be deposited, as well as on the other side, two low velocity or two smaller particles, no film will actually be deposited onto the substrate. So with that, the characteristics that we want to look at is nanohardness to see scratch resistance and resistance to ion bombardment, the dielectric strength, since in these dry edge chambers, they have the plasma ion flow. So we want to make sure it's electrically insulative to prevent electrical arcs occurring. As well as porosity, as I mentioned earlier, we want to have low porosity, have that green column, because porosity increases the erosion rate as well as decreases the dielectric strength, as well as have a low variation in thickness due to us wanting to have a even layer, being able to protect the material all the way across and having no weak points. So as Sam mentioned, NextEdge did sponsor a project last year, and so we're using that as a baseboard. And so, especially with their powder methodology. And so what we did is, or what they did that we're using is take the powder, ball mill it to reduce the particle size, separate using a sieve, and then bake out any moisture in the particles through the oven.
Okay, to begin the technical approach, we've kind of made a roadmap to give some context. So firstly, we used DOE to create and implement our experimental plan to actually do the experiments. Secondly, we tested the responses of each experiment using various methodology. And thirdly and finally, we analyzed these responses to determine an optimized recipe. Oops. So firstly, the DOE. We have a three-factor, two-level experiment where the first factor is carrier gas flow, represented by G in the table on the right. We had a low level of 10 liters per minute and a high level of 30 liters per minute. The second factor was stage speed, represented by S on the table on the right. We had a low level of 10 millimeters per second and a high level of 40 millimeters per second. And thirdly, we had the factor of deposition passes, represented by P on the table on the right, which had a low level of 10 passes and a high level of 30 passes. So these effects. Below is the really nasty looking equation. That is our general equation where we used our response or our calculated responses to back out the effects, which is represented by A. We have 8 different effects. And yeah, this is kind of just the under the hood of the DOE and what we actually did to develop and get our values. So our responses that Connor kind of laid the foundation on. So to test nano hardness, we decided to do nano indentation through INL using a Berkovich diamond tip. Secondly, we tested the dielectric strength of the material using breakdown voltage testing to the ASTM standard of D149-20. Thirdly, we tested the porosity of each spray or each experiment with a cross-sectional SEM image to the ASTM standard of E2109-01. And finally, we tested the variation in thickness with the same cross-sectional SEM to the ASTM standard of B487-24. So the SEM methodology. Up top in this image on the left, you can see this black layer, which we've identified as the substrate. Next, there's the darker gray layer, which is the anchor layer, as Connor mentioned. It is a very dense layer of powder and the aluminum substrate kind of mixing. Thirdly, we have the continued deposition, which, as Connor mentioned earlier, should be a less dense layer, but still YOF, still our deposited powder. And finally, at the bottom, we have our resin, which we had to use as a pre-processing step for SEM. So porosity, we did a qualitative comparison of coating to the ASTM standard that I just mentioned. And thickness, we took 5 thickness measurements at 5 different locations on this SEM image. We took the average and the standard deviation. And then finally, we calculated the coefficient of variation for thickness, which is standard deviation divided by mean. So our optimized recipe. As Connor mentioned in the background, we want a high nano hardness and a high dielectric strength. These are properties that need to be high for this coating to be used in the industry. And we want a low porosity and a low variation in thickness. So coating properties on the left, N and D, represented in the optimized recipe equation, and then coating quality, P and T, are both negative because we want them to be low values. So the analysis of our dielectric strength. Below we have a a bar chart of all of our experiments, 1 through 9, where B is our baseline experiment and C is our center point experiment. And we can see that the dielectric strength of experiment 8, which had a high gas flow rate, a high stage speed, and a high number of passes, had the highest or the lowest porosity. Excuse me. And the high, oh, sorry, had the highest dielectric strength. And we attribute this to a low porosity because the porosity and dielectric strength have an inverse relationship. And finally, we have a very low value of dielectric strength for experiment SP, which is experiment 7, which had a high stage speed and high number of passes. And we attribute this to a high level of porosity for the same inverse relationship. Next, we have our porosity measurements. We found a very high porosity for experiment GP, and we attributed this to the fact that there was not enough powder being deposited at once. There wasn't enough exposure on any given area of substrate at some time, so it couldn't condense. And we had a very low porosity for the same experiment GSP. And then, yeah, we found that there was enough exposure of the substrate to see the nozzle so that the powder could condense and form that anchor layer and have a higher porosity.
So we were also interested in the thickness of the coating. So in the graph on the right, I guess for you guys, or left for you guys, the overall thickness with the standard deviation is represented by the orange dots, and then the coefficient of variation is represented by the blue lines. So we found that the coating with the highest thickness was for high gas flow rate and high passes, and the coating with the lowest thickness was for high stage speed. And then variation, we found that the highest variation, which is what we don't want, was for stage speed, and it was lowest for the high number of deposition passes. So a little bit of analysis on this. We attributed the high thickness for the high gas flow rate and passes to a high enough particle velocity that adhesion is encouraged, and there are enough layers applied onto the coating that it levels out and makes it thick. And we attributed the low thickness for high stage speed due to the small amount of powder being deposited on each area at one time per pass. The variation in thickness, we attributed the high variation for stage speed as only the anchor layer is present, and the anchor layer tends to be uneven because as the particles hit the metal, it plastically deforms the metal as the particles fracture, and this can make the surface uneven. And we attributed the low variation in thickness for the high passes to the fact that as more layers are deposited on the substrate, it fills in voids on the surface to level out the coating. So we calculated the DOE results using these responses for each, which are shown in the graph. We wanted to maximize dielectric strength, so any effects that are positive are good. So you can see that increasing gas flow, increasing the stage speed, and increasing the number of passes is good for increasing dielectric strength. And we wanted to minimize porosity and variation in thickness, so negative effects are better. And you can see that both of these effects or factors are minimized for deposition iterations. So we input the effects we calculated into that general equation that Alex showed you guys earlier to find the optimal levels of all three factors for each response. We found that the greatest dielectric strength and also the least porosity occurred when all factors were maximized. And we found the least variation in thickness occurred when the gas flow rate and deposition passes were maximized, but when stage speed was minimized. So we wanted to optimize this recipe not just for each individual response, but also for the coating as a whole. So we created a z-score matrix using these DOE parameters to determine the levels that produce the coatings with the best combined characteristics. We input those z-scores into the metrics shown below and determined that the best recipe was when gas flow was 50 liters per minute, stage speed was 50 millimeters per second, and the number of deposition passes was 50. So a little bit of discussion. There were some errors in some of our methodology that we could have introduced. For breakdown voltage testing, we were only able to test one sample because breakdown voltage is a destructive process, or testing breakdown voltage is a destructive process, so we couldn't actually test one coating multiple times. It's also known that the approximate dielectric strength of YOF should be around 25 kilovolts per millimeter. And some of the values we got were much higher than that. So there was something with our method that probably introduced some error. For our SEM imaging, we also only cross-sectioned one sample. So there was not a lot of replicates there. For porosity, we only analyzed one cross-section per image. So it wasn't very representative of the whole sample. We were not able to receive our nanohardness data in time for this presentation due to scheduling conflicts with our contact at INL, but that should be coming next week. And then for the aerosol deposition equipment, there were some inconsistencies introduced if the nozzle was clogged or anything like that that we didn't notice when we were spraying. So sometimes the data we collected wasn't representative of just the factors we were changing, but other effects as well. And we would also want to take into account some time and material cost considerations when determining an optimized recipe. For example, high passes takes more time, so that might be not worth it for the amount of like dielectric strength they could introduce, for example. So in conclusion, a summary of our project, we took a DOE approach with a 2-level 3-factor design to understand how 3 separate parameters affected an aerosol deposition process. We characterized the coatings produced using nano indentation, SEM, and breakdown voltage testing. And we input these values for the characterization into a success metric to determine the coating with the best properties and quality. There are several directions we could take for future work. One would be to expand our DOE, test more levels to see if there's different effects that we didn't analyze. Other factors of interest include standoff distance, carrier gas species, and impact angle. Other responses of interest could be surface roughness or the etch rate of the coating in a fluorine environment. We would also want to improve our SEM analysis, so likely use an image processing software to quantify our porosity rather than our eyes. And we could carbon coat our sample before embedding it in resin or use a conductive resin to improve the quality of our images. We'd also want to do powder particle size analysis to ensure that the particles we're using by our methodology are the correct size for this process. Thank you guys for listening. Special acknowledgements to NextEdge, Jesse, Kiev, Dr. Jennifer Millette, and Dr. Harold Ackler. Are there any questions?
Good presentation.
Thanks.
So in the design of experiments, if I saw it right, you said your optimum was the highest of all 3 variables. Do you think you really captured the optimal deposition?
So that's kind of why we would want to expand the levels we're testing in our DOE. So we had 10 and 30 for gas flow and the deposition passes, and then 10 and 40 for stage speed. And we used this data to extrapolate, so we got a minimum and a maximum, but we would want to have more levels in order to see if eventually like the number of passes is negative to dielectric strength. So we could expand that way.
Okay. Another question. So your DOE should give you an idea of what the most influential process parameter is, and maybe I missed it, but what's the most influential process parameter?
For each response or the overall recipe? Overall, I believe was gas flow rate. Or stage speed, probably, because it increases dielectric strength the most, and it increases variation it increases variation in thickness the most, which is not what we want, but it is influential for determining the variation of thickness. So stage speed.
Any other questions?
Let's see. So it was all done at room temperature. Was there any consideration about temperature?
That's a great question. To be honest, so no, there was no consideration of temperature in the aerosol deposition chamber, but that is something we certainly would want to look at for future work.
Great presentation, guys. And I may have just missed this, but what were you looking for specifically qualitatively with some of your imaging?
Like the SEM?
Yeah.
Okay, so the ASTM standard we used was actually a qualitative analysis of one image, which was the ASTM standard versus our image. So that's what Sam was referencing when she said the qualitative part of our eyes.
Okay.
What? No, that's what he said.
Visual.
Yeah, it's a visual ASTM standard.
Okay.
So it's not the most scientific, but it is an ASTM standard that we follow.
Cool. Yeah, I was just curious. Thank you.
All right, good job, guys. Quick question. Were all your coatings the same thickness?
No, our coatings did have a variation in thickness throughout. That's just due to the different amount of passes we had resulted in different thickness between the different samples. So,
Do you think it would be worthwhile to normalize some of your results based on coating thickness?
I think that would be something great to look into. That definitely could give us some more accurate data for selecting the best overall coating, but that was just something that we didn't end up looking at, but that is a great idea because we didn't consider that. So
Good job, guys.
Nice job, y'all. Question about the nano indentation TBD work. Did you all discuss with INL of depth, load, what you want to do parameter wise for the testing? Or what's existing on the standard or whatever it might be?
We'd have to get in contact with them for that, but we did end up sending them our coating thicknesses from the SEM images we get. That's kind of what we gave them, but we didn't actually or ask them what ASTM standard they were using. That's definitely something we should know.
So lean on their expertise. That's fine.
Yeah, basically. They're experts.
Okay, thank you.
Hello, my name is Archer Kiritan,
I'm Jake Wessels.
and we are Team Platoon. We studied the closed loop PLA recycling and reprocessing. So our sponsor is Dr. Amy Mole. She's worked here for over 20 years. She's the co-founder of the MSE program and also the former head of the program. She's also the former dean of the College of Engineering, as well as was an associate director for CASE in the later 2010s. So as an introduction, one of the biggest challenges for using plastic products is waste disposal, especially with plastics like PLA. PLA is used on campus as beer cups, especially at like sporting events. And there's a huge lack of municipal recycling programs for this type of plastic specifically. So the goal was to develop a reprocessing method for recycling it.
So a little bit of background on PLA. It starts by being synthesized through the fermentation of plant starch to form lactic acid. In the States, it's most commonly corn. In other areas like Southeast Asia, sugar cane gets you your most abundant yield. This lactic acid dimer then undergoes a polycondensation process at temperatures below 200 degrees Celsius. This is also done with the presence of an azeotrope and done in a vacuum, both of which are to further enhance the water removal. So in your guys' image that you see on the left, this sort of shows you the two different products you could get, whether or not you use an azeotrope. If you don't use one, you're left with less water being removed and a consequent lower molecular weight PLA. It's not as strong, it's not as ideal. If you add an azeotrope, you lower the boiling point of the solution in general, get rid of more water, and you're left with higher molecular weight PLA, which is what you'll typically want. On the figure on the right, this sort of shows why you would want to do this polycondensation process below 200 degrees Celsius. If it's above this temperature, you do have an extra lactide step formation instead of going directly from lactic acid to PLA. It's not the worst thing, but it does hinder the efficiency of the process. So the actual beer pints that you guys have probably seen at Extra Mile Arena before are formed with a process called mechanical thermoforming. What happens is a sheet of PLA is taken above its glass transition temperature, placed between a plug and a mold part, and then the plug goes down as air is released to allow for cooling and for the solidification of this heated PLA in the newly formed pint mold. And it's immediately then sectioned off through machinery to mass produce it. Plastic extrusion was the name of the game for our project. We dealt a lot with it, and I'm just going to take you guys through some of the basics of it. So it starts out by taking some plastic feedstock and putting it into a hopper, and then a screw on the bottom is then used to push the plastic through a series of heaters. Now, these heaters must take the material above the glass transition and to the upper threshold of the melting temperature, so it's in a molten state. This is a part where you really do not want any excess moisture, as any moisture will likely boil, pop, and cause the integrity of your filament to be weakened. And on top of this, there must be a proper cooling method between the extrusion at the nozzle and the polar wheel so that it's not flattened by the polar wheel when it gets there. So PLA has really beneficial properties for making it easy to extrude. It was compared with ABS, PET, and PETG, which are three other very common thermoplastics used for 3D printing. And the melting point, processing temp, and extrusion temperature for PLA is lower than all of them, which is good for how easy it is to extrude. It takes less time to heat up your extruder and is just more energy efficient. On top of that, it has a much higher melt flow index than these other thermoplastics. This essentially means that you can get a lot more of weight of this polymer extruded in a shorter amount of time, more energy efficient for us, which is the name of the game for us. Unfortunately, it does also have some negative aspects, specifically with the water content. It has the ability to uptake up to 2.4% water, and it also has a resting equilibrium moisture content up to 2%. Both of these values are double the next closest one, so PLA does struggle in this regards. It also has a very large range of molecular weight, with lower weight samples being below 20,000 grams per mole and higher ones well exceeding 100,000 grams per mole. This means there's a wide range of temperatures that can be worked with and a large range of mechanical properties that will take. The higher molecular weight, the stronger it usually is, the longer the polymer chains, meaning more bonds that need to be broken in order to be deformed or impacted. So that is a good thing, but unfortunately, it also means that it must be worked with at a higher temperature in order to properly get it into a molten state. So this can be seen by this graph right here. The ultimate tensile strengths for PLA, a very wide range. I mean, 0.16 to 3,000 is more than triple the next closest range. And the modulus of elasticity is also a lot larger, with the exception of PETG being somewhat comparable. So to characterize molecular weight in polymer samples, what we typically do is use a process called gel permeation chromatography, also known as GPC. In this, PLA is dissolved in a solvent like oxalate or chloroform, and it is then forced through a chamber with a bunch of porous beads. Now in the solution, the polymer coils within the polymer are able to sort of coil up and form these ball-like structures. And the larger ones are not able to interact with the pores as well. So they are not going to be retained within this chamber for as much time, and they will move through a lot quicker. At the end of this, you'll typically find a calibrated sensor that's able to detect when these pass through. And this figure is a very idealized version. It's usually not going to be this linear, but you should see a negative correlation between retention time and the molecular weight, with the highest retention times being the smallest molecular weights of the sample.
And so basically you would expect a normal distribution similar to this, which can kind of tell you how many of what size molecular weight is a part of your plastic. So some current similar re-extrusion processes that are out there are done by companies like 3D Evo or 3Devo, I don't know how to pronounce it. They sell equipment like shredders, granulators, and extruders that are consumer grade, so people can do this at home. The difference though is that they are typically recycling old 3D printed parts or broken parts, not this thin plastic cup material that we're working with. So our goal is to establish a repeatable process to produce this quality 3D printing filament from those cups. This starts by acquiring our material, sectioning it into smaller pieces, shredding, granulating, and then finally extruding it into a filament. Once we have that filament, we're able to produce some 3D printed parts, and we can mechanically test the filament and the parts. So for acquiring the material, we got in contact with Extra Mile Arena, a team over there called Pints to Prints. They donated some PLA beer cups for us to use. That's the picture on the left or on the right there. It's kind of dirty cups. So we also purchased some pure PLA pellets called Eolas brand pellets online. We use that to test our shredding and extruding processes. All the cups that we received were washed with deionized water, no soap or anything, and dried with compressed air, and then finally stored in an airtight container so we can avoid moisture contamination.
So initially, we tried getting these section cups and placing them directly within the Philbot reclaimer, which was the shredder that we used. Unfortunately, what we found was that the plastic cups were way too flexible and thin and just sort of gummed up around the teeth of the shredder and didn't process properly. So we knew that going forward, we would need to somehow treat this material to either embrittle it or harden it or just make it more able to be cut properly by the teeth. So we decided to research the benefits of thermally treating it. And what we wanted to do was essentially heat it up well above the glass transition temperature of PLA. Now, when we do this, the amorphous regions of PLA, which is the majority of PLA, typically it's around 90% of PLA is amorphous. This allows these regions to have the polymer chains untangle, and then upon cooling, as you can see in the graph, it sort of becomes more solidified in a crystalline manner upon cooling. And that decreases the specific volume and consequently increases the hardness and brittleness. And at the same time, it also lowers the moisture content, which, as we discussed earlier, is something you want to try to do.
So we applied this to our shredding and processing optimization by thermally treating our cups. After sectioning them into smaller pieces, we weighed out about 150 to 200 gram batches onto metal trays and baked them for 1 hour at 150 Celsius. They're weighed before and after so we can see how much water we lost. And so this is the result of that. We found that the highest amount of water that all of our samples had was 1.45%, like initially, which is well within the industry standards for PLA, which goes between 0.01 all the way up to 2%. So to start our extrusion process, we started with the purchased material that we got, the EOLS filament, and we were using the Composer 350 made by 3Devo. As shown there. And we use the default parameters that came with the machine for 1.75 millimeter filament. This did not turn out super well. We had some non-uniform extrusion diameters and the filament was just unusable.
To sort of help us with this process, we downloaded some software called DevoVision that 3Devo offered, and this sort of tracked the diameter of the filament in real time. And once we did this, we set some higher and lower limits, about 1.8 to 1.7 millimeters. This was actually a stricter tolerance than the default is for DevoVision when you first download it. So we allowed ourselves a bit of leeway if it went a little bit above or a little bit below. And essentially, we just adjusted the heaters in the speeds of the screw and the puller to get to a point to where we were consistently producing filament that was 1.75 millimeter diameter, and all the parameters were in check. And going forward, these the set of parameters was used for all the new waste material. And this image that you can see on your guys' right is about a 33-minute window of proper extrusion. So we spent a lot of time doing this, months trying to get all these parameters correct.
So as for the parameters I was talking about, I kind of want to go over how the machine works a little bit more. So as seen on the diagram, there are 4 heaters in red that each have their own temperatures. So we have those in the table. There's also an extrusion screw that has a set RPM, or that we can determine. And then the puller wheels at the end, those are able to be set as well. So the main thing that we changed, though, was the temperatures, as we found that the material was just not melting very well. So we decided to go up to about 200 degrees, closer to the actual nozzle. So once we were able to finally produce some filament that was within diameter that we wanted, we created 5 samples of both the purchased material and our recycled material for tensile testing. We also 3D printed some specimens known as dog bones that are used for tensile testing. We did 5 of each of those in both materials. And we used the ASTM D638-22 engineering standard for testing the polymers at a rate of 5 millimeters per minute. So as for the qualitative analysis of our filament, we decided to go with this model of a 3D benchy boat. It's a little tugboat that has a lot of different details on it that are useful for just examining things like overhangs, small holes, how well or like how smooth the surface is, and overall aesthetic qualities. And here are the results from our tensile testing. We put all of our data onto one chart. As seen in blue and orange, those are the filament samples for both recycled and purchased. And then in black and green are the dog bone samples. You can see there's a big difference in displacement, and that's completely due to the gauge length difference between the samples. The dog bones were 10 times shorter at 33 millimeters than the filaments. We also measured the cross-sectional area. Since this is a force versus displacement chart, we also want to figure out stress.
And by calculating all of these values and individually charting them for the 5, we were able to get an average and a standard deviation just to see, how strong they pretty much are and how consistent the data was. What we found was that in general for the dog bone, standard deviation of highest one being 1.69, not that high, pretty consistent data. And the recycled dog bones, far outperformed by over a magnitude of 2 compared to the dog bones of the pure Aeolus pellets. On top of that, the filament for the recycled was also better than the pure Aeolus pellet filament, and it also had a smaller standard deviation, which means we were able to produce more consistent data with that. With our filament, the recycled stuff that we made from the beer pints being around 55 megapascals, it was slightly below the industry standards of 1.75 millimeter PLA filament that is available for commercial purchase. This is usually at 65 megapascals, but our recycled filament could be used comparably with ASA filament and is stronger than PETG and ABS filament based on their standards for filament. When we actually look at a piece that we printed, like the dog bone, we found that our 49 megapascal value is right within industry standards of 48 megapascals for other PLA dog bones that are also made with 100% infill grid patterns.
As for the qualitative analysis, the 3D Benchy boats demonstrated that this material can be printed into some useful aesthetic parts. The small overhang details were able to be added very successfully. The surface texture is very smooth, no under or over extrusion. The only shortcoming is that the very first boat we printed on the left didn't finish. The filament got caught in the machine because it got a little bit too thick with its diameter, which is why the diameter is so important. I was able to clip that and actually print a second boat pretty much flawlessly, aside from a little bit of stringing. So yeah, that's very successful. In conclusion, this PLA can definitely be recycled and repurposed into new products. It exceeds our expectations for strength and other properties, and it can be trusted to produce aesthetic parts. The only downside is that the material does need to be thermally treated before shredding to avoid clogging. For teams in the future hoping to do this project, we definitely recommend using the higher temperatures that we went with, as well as diving a little bit further into the molecular weight characterization using GPC. We didn't have enough time in our project to go over that, but we would have liked to see the results for that, as well as more in-depth analysis of the elongation and ductility of the materials.
Special thanks to our senior capstone instructor, Dr. Harold Ackler, and Dr. Jen Millette for writing revisions and content formatting, and Nathan Jones from Extra Mile Arena for supplying us with all of our PLA waste. Thank you.
Any questions? Yes, Sarah.
How did your guys' benchy boat compare to like the ideal benchy boat?
See, one of the hardest things about it is that our filament was, I don't know if you could see the model, it was passed around, but it's kind of clear. So it's kind of hard to see the surface a little bit, but compared to the ones that I've printed in the past, I think it looks awesome. It's kind of more of a qualitative analysis anyway, just to show like there wasn't any bubbling or any other issues, so.
What direction did you guys print the dog bones in? Was the filament vertical or horizontal?
So the dog bones are actually printed flat on the plate, and they were 100% infill with just like, it's called rectilinear infill.
Okay, cool.
So for before putting the shredded pieces into the extruder, you did the thermal processing, heating it up and then cooling it down. And the argument there is that by heating it up close to the melting temperature, after cooling down, we've got a crystalline polymer that's more brittle. Does it matter if you just cool it down enough? Can you process in a cold room, or like how much did heating up and cooling down help with the processing?
I mean, it was required to embrittle the material. As far as heating it up, we kind of we started out knowing we wanted to exceed the glass transition. The 150 degrees Celsius was actually, that was honestly the first just number we went with, and it really worked with us. And the cooling, as far as what we did, was just sort of, you know, over a duration of like a day. We typically worked with the materials a day after they finished baking. As far as like putting them in an actual colder than room temperature environment, we didn't do that. So I would not know exactly, especially about the rate of that as well.
And one other question, how do you get an azeotrope?
How do you purchase it? I think it'd be just like a solvent that you purchase, though I'm not 100% sure.
Cool.
Dr. Mueller.
Nice work. Good job. It looks like you have hit all the standards and the properties that you would like to hit. And I don't know, I didn't really get with what you compared this, but anyway, when you think about this is a successful process, how does it compare on the economic side? Did you estimate at all how much would it cost to process and recycle this compared to anything new?
So that's another thing is the cost analysis. I would recommend kind of putting on another team in the future. There's a lot of it that needs to be developed. The team at Extra Mile actually intends to get a larger shredder and a better extruder that's purely for these cups. So if they were to do that, I mean, there'd be quite a big budget for that. But overall processing the material wouldn't be super expensive, I would think.
This is a bit out of left field. Is there a difference in smell of the extruded samples from the recycled versus the pellets?
Actually, do you want to answer? Yes.
I mean, there was a little bit, yeah.
Okay.
That's pretty much it. Especially before washing, it's pretty bad. But
Yeah.
then you rinse
Yeah.
with DI water and blow dry, and it's pretty good.
Would it be something you would back of saying, yeah, Extra Mile, you can put this back out to serve to folks after?
Well, the
scent-wise?
3D printed parts we passed around were formerly beer pints, so they don't the actual.
So
part-
afterwards, it's like
Yes,
good.
yeah. Afterwards, it's fine.
okay, yeah. All right, cool.
To further on that, so it doesn't smell like beer, but when you do extrude it, it's kind of sweet. So that's kind of
Oh,
it's kind of
nice.
nice.
Added touch.
It's not unpleasant.
Yeah.
You know, get a little lightheaded, but you know.
Aha. Excuse me. Dr. Guignard.
Thanks. Just to follow up on Corey's question, like, do you know, or is there data on like compounds or plasticizers that would be leached into solution when using these
I don't-
before or after your process?
I don't think we found anything on that. Are you talking more like in the synthesis process or during the extrusion?
Post synthesis, like after you've
Oh.
made you processed it and made some new piece, you know, do the properties of the material change in terms of what they would be leaching into some solution in a container?
As far like you're talking about, like for maybe like food container, like some food containers, making it back for that.
Yeah. Better or worse? I don't know.
I mean, we started making filament out of this, and typically you don't really want to use 3D printed. You don't want to use a 3D printing process for food containing because the bacteria is able to seep within the layer adhesion parts. So I don't think we would ever make it specifically for a food containing product.
But also PLA is a pretty stable polymer. It doesn't tend to degrade as much as other polymers. So that can be nice. There's a little less leakage.
Thanks.
I'll try a yes or no question. This time. Nice job. And can you speculate on why the mechanical properties were different between or at least for the filaments?
So for the filaments, this was one thing that I wish we had a little bit more time. We would have actually made another sample of the purchase material because there was a little bit of diameter inconsistency with the first material, the EOLOS. But our recycled material was a lot more consistent. So that's probably why the standard deviation is so different and our strength is so much higher.
Just really hammering home that we definitely think it would be the like cross-sectional area of the EOLOS pellets. We did not fully perfect our parameter optimization yet for extruding by that point. For recycled, we did. So that's likely why we're thinking it would be stronger there. So we have that in this graph, and we have our gauge lengths versus the elongation. Obviously, for our dog bones, we had a much shorter gauge length, so they're not going to be able to elongate as much. But our filaments themselves, the actual EOLOS filament was able to elongate quite a bit more than our recycled filament. As far as to why that is, we were hoping for future teams to do more studies into that ductility and elongation aspect of it.
Thank you. Next up is our team sponsored by Micron.
Hello, everyone. There we go. We are Team MDP. I'm Ashley Redinger. This is Sarah Reedy and Luke Landsberg. And our project was determining gas behavior in ultra-high vacuum environments for atomic layer deposition applications. So starting off with our sponsor, it was Micron Technology, which is a major company within the semiconductor industry known for their computer memory and data storage solutions. Our sponsor from Micron was Dan Markowitz, who is an MTS pathfinding lead in Micron's corporate labs. And our faculty advisor was Dr. Stephen Hughes, who is a Cohen affiliate faculty, which means he supports research here at Boise State while also corresponding with teams over at Micron. So our project stems from a research collaboration between Boise State University's Atomic Films Lab and Micron Technology. The overall objective was to improve the current ALD system in the AFL for submonolayer deposition. The challenge with this was precise gas dosage. Therefore, our main goal was to refine the operating parameters of the AFL's doser system by focusing on studying gas behavior in ultra-high vacuum environments. Some methods include using a fast-acting valve to control pulse time and also controlling cross-chamber pressure. So let's start off with what standard ALD looks like. The key feature of ALD is its self-limiting nature. Which means that once all of the reaction sites on a substrate, on the surface of a substrate, are saturated and a single monolayer has been formed, the reaction stops. So starting at step one, starting at step one, as we can see, precursor one is pumped into the chamber. It is allowed to react with the surface of the substrate and form a full monolayer. Once this monolayer has been formed, it is purged and pumped from the main chamber, and precursor 2 is introduced into the chamber. This precursor is then allowed to react with the monolayer formed in the previous step, and then this is also purged and pumped from the chamber. And this cycle continues until a target thickness, a thin film thickness has been achieved. So our project is more so looking to enable submonolayer ALD, which means that an incomplete monolayer is formed on the surface of the substrate, as we can see in image A, as compared to the fully deposited substrates in images B and C. Submonolayer ALD requires very extremely small amounts of gas being inputted into the main chamber. So that is why we were looking at ultra-high vacuum environments for this. And it's important for research as it better reveals the reaction mechanisms behind ALD, allowing for better comparison to computational studies which involve one to few molecules interacting with a small portion of the substrate.
Okay. All right, to dose the precursor molecules into a UHV chamber, a pneumatic valve will be open for a short dose time of delta T. Molecules emitted from the valve can be calculated based on the flux of the precursor molecules against the orifice of the valve and the dose time. So according to kinetic molecular theory, the impingement rate of molecules in a gas striking a surface is given by the Hertz-Knudsen equation on your left. And so M is the molecular mass, K is the Boltzmann constant, T is temperature, and P is pressure. So when an orifice of area A is open for a time T, you can then calculate the number of molecules emitted given by this precursor dosing equation on the right. And so where NE is the number of molecules emitted. And from this, you can see that the number of molecules is directly proportional to the cross-chamber pressure and the dose time. So by taking the partial derivatives of the precursor dosing equation in respect to the changing variables of pressure, time, and temperature, we can find out some relationships. So for both pressure and time, as those variables increase, the number of molecules will also increase. The relationship is also linear and directly proportional. However, for temperature, as temperature increases, the number of molecules decreases, and this will do so rapidly, and then it is also inversely proportional. You can't hear me? Okay. Sorry.
By taking the partial derivatives, we can use these to find the uncertainty in molecules emitted. So the uncertainty is DNE, and DNE can be calculated by taking the magnitude of the partial derivatives with the changing variables. So not only can we calculate the number of molecules emitted based on the precursor dosing equation, but we can determine the uncertainty in the number of molecules or the give or take of how many molecules we expect to be emitted.
All right, so here's our actual system in the AFL lab. So it consists of 4 main parts, all based around this central cross chamber. So on the right is a thermal expansion / leak valve. This connects the cross chamber to our nitrogen gas source. And it uses thermal expansion to really control the orifice size and just allow a very precise amount of nitrogen gas into that cross chamber, which pressurizes. On top of the chamber, there is a pressure sensor, so we can determine that what that P is. And then on the left, there is a fast-acting ALD valve. This is a pneumatically controlled valve, and it opens very quickly and allows a short burst of nitrogen gas to go from the cross chamber into the main chamber. So regarding these variables that Sarah was talking about, the P refers to that pressure within the cross chamber, and that delta T refers to the time that ALD valve is left open, and we call this the pulse time. So here's another schematic of our system. We've got the cross chamber and the main chamber. Before the cross chamber is filled with nitrogen, it is evacuated, so there's no air contaminating it. It's just pure nitrogen. This is in the millitorr range, so we can use the barytron pressure sensor, which is an electromechanical system. Because we're not in ultra-high vacuum yet, we can use a much simpler pressure sensor. But in the main chamber, this is ultra-high vacuum, so we use an RGA pressure sensor. This is a residual gas analyzer. And it's basically just a small mass spectrometer. It ionizes the gas, and then it counts the number of nitrogen molecules based on their mass. So a small amount of that nitrogen will flow through that fast-acting ALD valve into the main system, and then we'll analyze the pressure difference. So our whole process is based on these 2 operating parameters and how they affect the gas dosage. So we have the pressure within the cross chamber, and we varied that between 0.05 and 5 millitorr. And this was just based on the barytron pressure sensor. This is the range that worked with it on top of that cross chamber. And we also have the ALD valve timing, or the pulse time. And we varied that between 5 and 1,000 milliseconds. We went down to 5 milliseconds because that's kind of the limit of the operating limit for the ALD valve we used. It can only open and close so quickly, and went down to around 5 milliseconds. So our original hypothesis was as we got to that extremely low pulse time, reaching the limits of that valve, we would get low precision because just mechanical inconsistencies within the valve when it's nearing the limits of its specs. To investigate this hypothesis, we did a couple data analysis methods. We did DOE. This gives us really the magnitude of the effect of each of these parameters on the resultant gas dosage. And we also did a RSD analysis, a relative standard deviation. This is simply the standard deviation divided by the mean to sort of normalize it. And this gives us a way to look at the precision and consistency of our gas dosage compared to the various parameter levels. So here's what our data looks like when it pops out. We have the various pressure spikes resulting from our increasing pulse times. Once we get this data, we would integrate under these pressure spikes to get the total change in pressure. And then just using the ideal gas law, we would relate that change in pressure to change in moles and the number of molecules emitted. We did 5 trials for each pulse time of sub 50 milliseconds, and then 3 trials for the 50 to 1,000 milliseconds to get a good standard deviation measurement.
Okay, as for our DOE, we decided to look at both cross-chamber pressure and pulse time, as we've discussed before, basically to determine the impact of these variables on the number of molecules emitted into the main chamber. So first off, we chose 2 cross-chamber pressures, 0.5 and 5 millitorr, to stay within the range of the RGA sensor, and also 2 pulse times of 50 and 100 milliseconds in order to test the more mid-range pulse times that we were going to look at. So in this general equation that is generated from the DOE matrix, NE is the number of molecules emitted, A naught through A3 are the effects that are calculated from that matrix, P cross is the cross chamber pressure, and delta T is the pulse time. And as for that, those results from the DOE, as you can see from the generated equation, the cross chamber pressure has an impact 6 orders of magnitude greater than the pulse time. And we will get into that more later.
Okay, so here you have an illustration of the distribution of the gas pulses by pulse time, specifically at a cross chamber pressure of 0.5 millitorr. So the blue dots represent all the individual data points, and that orange dot there is the mean of the data set so that you can see the distribution. So as you can tell that the distribution varies significantly by pulse time. So shorter pulse times tend to have a more consistent result, while the longer pulse times showed greater variability. So this variability in longer pulse times suggests that maintaining precision in gas dosage becomes a challenge when the pulse time duration increases. So here we have the relative standard deviation values plotted on a logarithmic scale. So the values, so below 30 milliseconds, these RSD values are relatively low. Beyond 30 milliseconds, they increase significantly. They exceed about 10%. So again, these higher RSD values at longer pulse times indicate that precision diminishes as the pulse time duration extends. I would also like to mention that we did perform a Grubbs test to identify any outliers in our data. And throughout all the data sets, only the 30 millisecond data set identified a low outlier, and that data point was thrown out before we performed the statistics on it. Okay, so here we have the relationship of pulse time versus number of molecules emitted. So initially, the number of molecules emitted rapidly increases, and then as you can see, as the pulse time continues to increase, the rate of increase in the number of molecules starts to slow down. So this variation in the emission rate could be due to the efficiency of the pneumatic valves opening and closing times, depending on the pulse time, or there's the fact that the gas behavior may be changing altogether. So as I earlier mentioned, the relationship between pulse time and the number of molecules emitted should be linear based on that precursor dosing equation. However, the data shows that in actual applications, the rate may not be perfectly linear. And lastly, we have the impact of cross-chamber pressure on the number of molecules. So as cross-chamber pressure increases, the number of molecules increase, which is good. This was predicted by the kinetic molecular theory. However, unfortunately, due to time constraints, we were not able to gather the data, the appropriate data that we could have ran more statistics on and better analyze this relationship between cross-chamber pressure and the number of molecules emitted. So I would also like to point out that throughout all of our data sets, there are crucial points missing from some of those center regions of our range. And so it would probably have been, if we had had those, our results could have been more definitive.
All right, so regarding that initial hypothesis that the smaller pulse times would lead to lower precision, the data actually showed that that was the opposite was true. So these smaller pulse times had the best precision. So we looked at the data for a while and we came up with a new hypothesis that the reason that the longer pulse times didn't have a good precision was due to a change in pressure differential during the dosing. So the cross chamber pressure, the cross chamber and the main chamber have different pressures, and there's a differential between them. This is what causes the gas to flow in the first place. But as that ALD valve is left open for longer periods of time, this gives more time for the gas to equilibrate, and the pressure differential changes during the dosing. And we've attributed that to a greater variation in the gas dosage at longer pulse times. As Sarah was showing, we have the RSD minimized at 10 milliseconds, and that was the greatest precision out of all of our tests. So regarding these findings, this is actually quite promising for future submonolayer studies, as contrary to our expectations, the precision was not compromised at these low pulse times. So this will allow us to do relatively consistent nanomolar doses at these 30 milliseconds and lower pulse times. We also found that the cross-chamber pressure was significantly more impactful than pulse time on the gas dosage. So for these submonolayer studies, that's good information to have, so they can really focus on that cross-chamber pressure when they're trying to get these nanomolar doses. For future work, we want to further test our findings with a more refined DOE. We also want to look at the experimental impact of temperature on the dosage, and then also examine the theoretical coverage of a wafer, given that the wafer is some distance away from the orifice.
Thank you to our faculty advisor, Dr. Stephen Hughes, our sponsor, Micron and Dan Markowitz, and then also Angel Conrado and Dr. Ellen Grignard in the Atomic Films Lab, and then, of course, our MSE 482 instructor, Dr. Harold Ackler, and Jen Millette for all of her writing expertise this semester and year. So. Yes, I did. Yes, I did.
Thank you. Nice. Any questions?
Jen
for the-
Millette is a doctor, just in case I forgot to say that.
Thank you for clarifying.
This is such a cool project. It's a thermodynamicist's dream to open a valve between an empty tank and a full tank over and over and over again. I'm curious if is there an analytical solution to the change in pressure as a function of time when you open this valve? Is it possible to predict that that decay or the difference in the precision with the longer openings?
Yeah, regarding that difference in precision, I don't believe there is any like theoretical like equation or anything regarding that. Yeah, so I'd say no. There's not really a good way to analytically determine that. Yeah.
Thanks for the great presentation. It's so exciting to see the results. And really cool that the short dosings work really well. Do you know, I thank you for plotting the number of emitted molecules. That was awesome. Do you know how many were in the ballast chamber before the pulses?
So we don't have we have the volume of the main chamber, which we use to find the molecules emitted via ideal gas law, but we don't actually have the volume of the cross chamber. So we were not able to find the number of molecules in there.
Thanks.
Good presentation. I guess kind of like the question I asked this earlier group was, what's the most influential parameter, and then your biggest source of error? I know you had the error propagation equations that you used. What's your biggest contributor, and is that a important, like, can we buy a better something to make that error less to improve our results?
Oh, buy a better something. I don't know what, before you said that, what I was gonna say, is we actually did notice in our data that the base pressure that is in the main ultra high vacuum chamber, if that is slightly off, it does affect the number of molecules that are going into the system. So as far as our data goes and like the error that we might see in that, I do feel like that one was a large contributor. As far as like pneumatic valves and things, we do have one of the better, like, very specific swage lock ALD valves that are made precisely for this process. But if my team wants to add anything else.
According to our DOE, the most impactful parameter was cross-chamber pressure as well, but we were unable to further determine the variation within different cross-chamber pressures due to time constraints.
Nice presentation. It's an interesting observation that this gets more precise at shorter pulses, and your hypothesis that this is due to equilibration of the pressures, the pressure difference. You could test this if you had not just change the frequency of pulses. Let's do 5 milliseconds pulses and do them at different intervals. So let's say after a 5 millisecond gap or a 10 millisecond gap in between, and repeat that. Did you think about that, doing this, that you could test this hypothesis?
If I understand the question correctly. So we did our first run, and we noticed that some of our peaks were being affected because we were not leaving enough time in between the doses. So after analyzing that data set and realizing that, we did start leaving exactly 15 seconds in between each pulse that we allowed into the chamber. Does that answer your question? Sick.
Just want to confirm that's not main chamber pressure, right? Because that's the opposite of a vacuum.
That is correct.
Okay.
We forgot to change
No,
that.
that's
I
good. All right.
apologize.
Just
That
wanna make
is
sure I was like,
actually-
you're not getting a vacuum. That's all.
that is number of molecules emitted. I apologize.
Anyone else? Well, thank you. Our final talk for the day is a project sponsored by INL.
Good afternoon. We are Team Pebblebed Patriots. My name is Sarah Cole, and my colleagues are Lauren Estes and Noah Montrose. And our presentation is on measuring thermal emissivity of nuclear-grade graphite. Our sponsor is the Idaho National Laboratory, the nation's leading nuclear research and development site located in Idaho Falls. Our INL mentor is Arvin Cunningham, staff engineer and scientist. And our Boise State mentor is Dr. Brian Jaquez. Graphite serves 4 key functions in high-temperature gas-cooled reactors. 1, a neutron moderator. 2, a core structural material, like you see here in this image. 3, as a reflector. And 4, a heat sink. Specifically, during thermal transients, which is an instantaneous increase in temperature, graphite serves the function of wicking heat away from the fuel via radiative heat transfer. The property associated with this is called thermal emissivity. The Idaho National Laboratory provided us 6 grades of nuclear graphite to study, and we were interested in 2 key areas of interest among these. The first was the microstructure, specifically grain size, and the second was oxidation. So first, starting with microstructure. As we see here among our 6 different grades, there were several different forming methods used to create these graphites. If we look at the top, the ones that are outlined in red include IG-110, ET-10, and 2114. These were all formed via isostatic molding, which is a uniform application of pressure on all faces of the graphites. This resulted in relatively fine-grained microstructures between 10 and 40 micron grain diameter. Then on the bottom row, we see grades NBG-18 and NBG-17, which were formed by a technique called vibrational molding. This is similar to the image shown there of compression molding with uniaxial pressure applied on 2 faces of the graphite, with the only difference being the base is vibrated to increase the packing efficiency. And then the final grade was PCEA, which is formed by extruding graphite paste out of a specific shape. Now, these bottom 3 resulted in relatively coarse grain graphite between 100 and 1600 micron grain diameter. And we hypothesized that the more coarse grain graphite would result in higher emissivity due to increases in, porosity, which would increase the surface area for higher emissivity. Now, the other area we were interested in was oxidation. Inside the nuclear reactor core, there can sometimes be minor air ingress, which, because high-temperature gas-cooled reactors are operating up to 1,000 degrees Celsius, this will oxidize the graphite, and so we want to have some insight into how that will impact the emissivity.
All right, so what is emissivity and why is it important? As Sarah said, moderators in the nuclear reactors are made of graphite. The reason why they're made of graphite is because they have a very high emissivity. Now that means that they're able to transport heat very efficiently. And emissivity is a measurement of that efficiency. It is pretty much shown as the total emitted power of your material over a perfect ideal emitted power of a black body. A black body has an emissivity value of 1, which means that that's as good as it gets. And that's actually not realistic in the real world, and I will get into that in just a bit. All right, so the physical laws that govern emissivity have to do with radiation. Radiation, such as the Stefan-Boltzmann's law. Now, this law shows that the total emitted power of a material will increase with the Stefan-Boltzmann's constant sigma multiplied by the temperature to the 4th power. So very quickly with temperature. And then that is across all spectrums that you're looking at. But if you want to find total emitted power at a specific wavelength, you're going to look at Planck's radiation law, where you can find the total emitted power at a, I don't know with lasers. Oh, there it is, at a specific point on the wavelength. So if you want to find the point where it peaks, the total emitted power peaks, you're going to use Wien's displacement law. And that is in that little right there. And as you can see, at higher and higher temperatures, your wavelength is going to shift lower and lower where the total emitted power is. All right. Oh, yes. So how, the factors that influence emissivity, as I said, temperature and wavelength, but nothing is ever perfect. It's never actually one. The factors that affect it are things such as your grain direction and isotropy. This is very understudied, and we did want to address this in our study. But additionally, you also have your material composition. Metals have a very low emissivity, and non-metals have a high emissivity, hence graphite. And then additionally, your angle of incidence, that the electromagnetic waves are going to emit from your material, depending on the direction that your detector that you use, it will influence your emissivity measurement. And then lastly, surface finishes, conditions, cleanliness is huge on emissivity. So on the left here, we have a very rough surface of graphite, i.e. maybe a oxidized sample. This will have a higher emissivity because there are more cavities for incident electromagnetic radiation to absorb into the material. Versus a smooth surface, you're going to have just one chance to hit the surface and absorb into the surface, so usually less emissivity. Now, to measure emissivity, there are various ways to do it, but one of the simplest ways that we could feasibly do it is using an IR pyrometer. The benefits of an IR pyrometer is pyrometers measure infrared radiation at just 8 to 14 microns in the spectrum. This is important because that is where atmospheric conditions are very, very minimal. So in this graph right here, we can see at 8 to 14 or 8 to 16 in this case, the transmission of air is really high. So we're not going to have the effects of the Earth's atmosphere influence our measurements. Additionally, a pyrometer works by you have your object that is radiating emission, and the optics pick it up and the sensor transforms it into an electrical signal, which is calibrated in the pyrometer to be a set temperature. So with that temperature, we're able to see the surface emission temperature being radiated. In our setup, we have an implanted thermocouple, which Noah will get into in a second, inside of our sample to see the total temperature that has been absorbed. So if you can see how much temperature is absorbed and how much temperature is emitted, you can see the difference between the two, and the pyrometer can calculate your emissivity value.
So before we start getting into any part of the experimental setup, we first need our samples made. So all of our samples were manufactured at the Idaho National Laboratory IRC complex in 1-inch cubes. There were two main reasons for choosing the cubic geometry. The first and most important reason was we needed flat faces for our emissivity measurements. And the other reason was we needed a nice flat base to prevent our sample from rolling around in the experimental setup. On the bottom right, we can see the difference in isotropy within our samples. Our IG-110 was the isostatic press sample, has this nice even structure on all faces, while versus our PCEA, it has a preference with the grain direction, so we can see our against grain direction and our with grain direction. All of our samples did have holes drilled within them in order for the implantation of a type K thermocouple, which allowed the measurement of the true temperature of the sample. Our radiative measurements are taken on the opposite side of this thermocouple. Now getting into the pyrometer that Lauren started to discuss in order to measure the radiated heat or the surface temperature of our sample, there are some things we need to take into account. Something nice about our pyrometer is it had a laser sight. So what we can do is we can make sure we're looking at the same point every time between all of our measurements. And then something we need to take into account is the spot size. So the spot size is essentially what our graphite is looking at. And we want to make sure, or that what our pyrometer is looking at. We want to make sure that we're looking right at the graphite. For us, we want the minimum spot size in order to make sure if there's any differences in like bumping the pyrometer or some movement within the sample, we want to make sure that we're still looking at the graphite. So we purposely distance our sensor 61 centimeters away in order to get that minimum 9mm spot size. This is a little cartoon that we showed last semester of what we predicted our experimental setup to look like, in which we have our graphite sample sitting in the center right here with an alumina plate supporting it to get it in that viewing distance. On the right side, we have a custom end cap with our thermocouple in to get the true temperature of the sample, as well as gas lines flowing argon through the system. The reason we're using argon is graphite will oxidize around 400 to 500 degrees Celsius, so we want to make sure that our graphite still remains in the sample and we don't open it to find nothing at these elevated temperatures. A unique property of argon gas is due to its monatomic structure. It is incapable of absorbing the IR radiation. On the left side, we can see the IR pyrometer looking through a zinc selenide window into our sample. We chose zinc selenide because it has a constant transmission across the 8 to 14 micron wavelength window, which made our calculations much easier versus, as we saw on Lauren's side, the high variations in some other transmittance curves. So here we can see our actual test setup compared to our cartoon, and we can see we were pretty spot on in how we expected it to be. The only difference we had was the addition of the mass flow controller we can see at the bottom to help regulate the amount of argon gas flowing into our system to prevent that oxidation. Now, making this setup wasn't all sunshine and rainbows, as specifically the viewport and this custom port over here did take some time to manufacture. After consulting with the machine shop, we chose the best machinist in the building, Dr. Harold Ackler, to do all of our work. And we had Connor Berry from the EIS help weld all of our flanges. So as we can see at the very top, our custom gas in, gas out, and thermocouple in port. And at the bottom, we can see where our zinc selenide window will attach to look into our graphite. Now, with making a custom setup, we need to see any errors introduced into our system. We need to essentially validate our system. So there's some things that we need to address. First is we need to understand any issues with our IR pyrometer beforehand by verifying it against a black body calibrator. Next, we need to understand how the effect of the transmission of the zinc selenide window will affect the results by just introducing it in between the pyrometer and the calibrator. And finally, we want to compare our Type K thermocouple that we purchased against a NIST or already calibrated Type K thermocouple, which was provided by the Advanced Materials Laboratory. So what we can see is there is a very significant difference in the sample temperature and the recorded sample temperature. So what we can see is for our black body calibrator, if it's set the true temperature to 500 degrees Celsius, we will really only be recording around 447 degrees Celsius. So we did need to take this into account. And with this high R squared value, we were able to interpolate this to the higher temperatures that we recorded at. Similarly, looking at the Type K thermocouple, we were very pleased to see that there was very little difference between the NIST traceable and our purchased Type K thermocouple. It is worth noting around 850 to 900 degrees Celsius, we did receive a maximum variation on the order of 7 degrees Celsius. But however, before this 800, the 400 about 850 degrees range, we did only see a maximum variation of on the order of 1 to 2 degrees Celsius.
Earlier, I told you we were interested in 6 grades of nuclear graphite, but we narrowed the scope of our presentation to focus on the fine grain IG-110 that was formed via isostatic molding and the coarse grain PCEA formed by extrusion. In addition, we were delivered an IG-110 sample that was oxidized to 5% mass loss and a PCEA sample oxidized to 2% mass loss. We didn't have 5% because the PCEA took a lot slower to oxidize at 500 C, and that's what we got from our sponsor. This is a summary of our experimental results, where we show thermal emissivity versus temperature. I'll draw your eye to the yellow curve and the red curve, which represent the difference in emissivity between 5% mass loss and 0% mass loss IG-110. Our results align with our hypothesis that the oxidized graphite would have higher emissivity. Sort of as Lauren mentioned earlier, the logic there is that the mass loss will produce coarsening in the sample that will increase surface area for incident electromagnetic radiation, if not absorbed the first time, to sort of ping pong off of itself, off of all those little curvatures until it's finally absorbed and re-emitted, thus leading to higher emissivity. The same trend was true for the PCEA, which is the 2% in blue and the 0% in green. But the trend we did not expect is that the fine-grained grades actually had higher emissivity than the coarse-grained. But the reason, our sort of like initial thoughts about why that might be is that the starting carbon source and the proprietary blend of filler versus binder particles may actually have more of a role in emissivity than the microstructure and grain size does. For IG-110, we compared our results versus a paper by Chai et al. From 2020, which had a very similar experimental setup. Our work is shown by the solid line and the Chai paper is by the dotted line. And what we saw is that our emissivity was measured about 0.04 higher than that study. This represents about a 5% error in comparison to theirs. But as Lauren's about to show you in our error analysis, we think that two major errors may lead to these differences. Number one is the inability to have a true isothermal soak in our system before we took our test measurements, and Lauren will get a little bit more into that. And the second is the inability to really have a stabilized pyrometer when we click or shoot the heat gun at the sample. And we think that these may have led to an artificially higher emissivity readings than actual.
All right, so error analysis was very important to this project because measuring radiation is very sensitive. So our main source of error has to be the pyrometer, and there's a lot of reasons for this. Pyrometers, I mean, you barely poke the thing and it kind of like fluctuates like 10 degrees Celsius. So the best way to do that would be to stabilize our pyrometer and maybe get a more advanced pyrometer. I would also say we would get it professionally calibrated due to manufacturer settings. We were not able to do that ourselves. And then also noise in the environment always is affecting it. A lot of other studies, like the one that we talked about earlier, that study was not done in a furnace like us, so there might be slight errors with that. Additionally, a source of error that could be within the furnace could be the fact that we are going up to 1,000 degrees Celsius. We don't necessarily know how argon acts at lower temperatures versus very high temperatures, which could cause some differences in our setup. However, other experiments were not done under the gas that we did, and they still saw some similar trends with emissivity. So lots of thought in performance improvement for the future. And then additionally, there could be surface differences of our samples compared to other samples. We don't know, for example, how these specific graphite samples were formed fully, since it is a proprietary information. We don't know the exact raw materials, so it's difficult to compare. But improvements in the future, I guess I could go to that in this slide, but like the future work of this project would be to improve the pyrometer so that you could have better readings, but also do more test measures. As we tried to mitigate error following ASTM standards, we were unfortunately not able to finish 3 runs per sample. We were only able to do 1, so that would be improvement in future work. Additionally, we want to analyze the effects of isotropy. That was an initial objective, but we unfortunately ran out of time with that. But we would like to see, since it's very minimal amount of research right now on the effects of isotropy on emissivity, that would be very exciting to look at. But overall, this project was still able to address some knowledge gaps in the nuclear industry for specific grades of nuclear graphite. And thank you to Idaho National Laboratory, our sponsor, and Boise State University for a great education. Thank you so much to Arvin Cunningham, our awesome sponsor, and Dr. Brian Jaquist for asking us the hard questions as his faculty advisor. Thank you to Dr. Jen Millette for your writing expertise and presentation of all of our things. And Dr. Harold Ackler, our professor and the use of the materials teaching laboratory. And thank you to Connor Berry for all of the awesome work he did for our flanges. Thank you. Questions?
Thank you. Well, you're close, so.
Great presentation, team. I'm curious, you had a hypothesis about how the surface roughness would influence the emissivity. Could you scratch one of these samples with coarser and coarser sandpaper and test that to check that hypothesis?
Possibly. The issue with that is graphite will, when you sand it down, since it's so porous, and so, you think about lead pencil, how quickly it kind of like, I don't know what the word is, but it'll fill in those pores and not necessarily be a true surface roughness. We were talking with INL, and we think the best way to try to create consistent surface roughnesses within samples is do some sort of like flash oxidation to try to control it. But yeah, sandpaper would probably give you misleading results. Anyone else have something to say?
Estrada?
Thank you. Really nice presentation. I'm curious, did you think about doing this under vacuum to prevent any convective heat losses? And would that impact your measurement at all, or what's the contribution of conduction, convection, and radiation?
We thought about that because some people in INL, some cool expert scientists, gave us the idea that if there's turbulent flow or something of the argon gas at high temperatures, my first thought was like, okay, what if we did it under vacuum to like look at that theory? Originally, why we chose argon gas was to prevent oxidation of the sample, as well as to try to simulate a high temperature gas cooled reactor, since they're not under vacuum. So that was kind of our thoughts on that, but you guys have something?
It would have been very helpful, I would agree, like to do the measurements under vacuum to understand any convective heating effects of the turbulent flow of the argon. But specifically for our test setup, it wasn't specifically airtight. We did need to move the thermocouple back and forth in order to load the sample in and out. But we did measure the mass loss between each run, and we found that we were running enough positive pressure that there wasn't any oxidation. But if we did run a vacuum system and there was any form of leak, our sample would likely oxidize.
Any other questions? You want? Well, I'm here.
Can you think of a technique to quantify any oxidation that you might have been able to characterize your samples with?
The one prominent way is mass loss, is just measuring the mass of the sample before and after. A formal characterization technique that I've seen is Raman spectroscopy, and seeing how like the different vibrational modes can identify surface roughness, but not hand wavy.
Brandon?
I apologize if I may have missed this, but I noticed you guys compared your emissivity values of your graphite specifically to a study in 2020. I was curious if there were maybe some industry standards of the emissivity values of that graphite, and how do your values compare?
There isn't any industry standards. That was the big search for this project, was really to provide some sort of value. The thing about emissivity is it's always a comparative value, and it's very difficult to come across a specific standard because there's so many effects that like a slight change in material will drastically change your material. Although we had the same material as the IG 110, right, it was IG, not the PCA. Our hypothesis and why it could be different was they had a slightly different test setup. They used an electrode to heat up their sample versus we had a furnace. And they also calculated their emissivity versus using a pyrometer to calculate it for them.
Yeah, so is the study in 2020 then the only basis of comparison you have?
No, we had a couple different papers that we were able to kind of look at that had some similar. There's not a lot out there, but if you look like speak to it.
Sure. Some of the other papers we looked at only had data up to 500 degrees Celsius, and we started at 400 and went up to 1,000. But for that specific paper that was IG 110 at 500 degrees Celsius, their emissivity was 0.5, so it was significantly lower. But the reason we compared it to the Chai 2020 paper is it had a very similar experimental setup as ours in the way that it calculated emissivity. So we're unable to speak to why we're not getting the emissivity of 0.5 that other papers did, but we saw a wide range of emissivity values for the same graphite grade across literature.
Thank you.
You guys mentioned that you found the fine grained structure to have a better or higher emissivity than the larger grained one. Have you guys thought that that might be due to like a larger amount of grain boundaries with like disordered bonds, stuff like that?
Yeah, we actually did have that exact discussion, but we then thought that it probably came down to the exact composition of the graphite might play a more dominant role than like greater surface area for more grain boundaries. But yeah, we were kind of thinking in that line.
I think one way to like look into that in the future would to do SEM images of the surface to really see what's going on there. I think that would be really cool. That was my thought on that.
Anyone else? I need the exercise, believe me.
No, you do not. You look great. Okay, so a question about the composition with SEM. How do you get composition out of SEM? Just
I wasn't
Yes.
sorry. Yeah, EDS of course, but I was more meaning just like what does it look like?
is EDS a trustworthy tool to look at stuff like carbon and oxygen?
No.
Okay,
No, we can't look at light elements with EDS.
very good. Okay. But yeah, it would be really cool to see the roughness and stuff. Yeah, no, it's good. Yeah. All right, what help? Yep.
Should we keep them here a little longer? Thank you. And thank you, everybody. There are no other issues. I think that is it. Again, I want to thank our sponsors. Most of them are here. Greatly appreciate your support and working with our students and supporting our programs. Thank you.